Welcome to the lesson on chords of a circle. At the end of this lesson, you will be able to prove that a perpendicular drawn to a chord of a circle from its center divides the chord into two equal parts. You will also be able to prove that equal chords of a circle are at the same distance from the center of the circle, and equal chords of a circle subtend equal angles at the center of the circle. One day, three friends A, B and C decided to have a race. They made a starting line ABC and decided to run to their common friend O. Who do you think won the race? A, B and C are all very good runners, but B won the race. Now let's see if B had any advantages. Aha! So B had the advantage of running the shortest distance, but they were all running from the same straight line. So, how did this happen? B ran along the perpendicular line from O to AB. The perpendicular from a point to a line segment is the shortest distance between them. It is also defined as the distance of the point from the line segment. Next, we'll discuss a theorem based on the perpendicular bisector of a chord. The theorem states that the perpendicular from the center of a circle to a chord bisects the chord. Now, consider a circle with a center O, such that AC is a chord of the circle. OB is perpendicular drawn from O to AC. We have to prove that OB bisects the chord AC or divides it into two equal parts so that AB equals BC. Let's join the lines OA and OC. Consider triangles OBA and OBC. Since OB is perpendicular to AC, triangles OBA and OBC are two right-angled triangles. Further, in triangles OBA and OBC, OA equals OC, since both are radii of the given circle. Note that OA and OC are also the hypotenuse of the right-angled triangles OBA and OBC. OB is common to both the triangles. So, by the RHS congruence rule, triangles OBA and OBC are congruent. Congruent triangles have their corresponding sides equal. Thus, AB equals BC. Therefore, B is the midpoint of AC. This means that line OB divides the chord AC into two equal parts or bisects it. So, our theorem is proved. Now, let's see if the converse of what we just proved is also true. The theorem states that the line drawn from the center of a circle to bisect a chord is perpendicular to the chord. Consider a circle with center O and a chord AC. Let us draw a line OB so that it bisects AC. Now, we have to prove that OB is perpendicular to AC. Let's join OA and OC. Consider triangles OBA and OBC. In these two triangles, it is given that AB equals BC, since OB bisects AC. OA equals OC, since both are radii of the same circle. OB is common side to both the triangles. So the triangles OBA and OBC are congruent by the SSS congruence rule. This also means that angle OBA equals angle OBC, since congruent triangles have their corresponding angles equal. Angle OBA and angle OBC are equal and together equal to the straight angle ABC, which equals 180 degrees. This means that angle OBA and angle OBC are both right angles. This also means that OB is perpendicular to AC. So the theorem is proved. Look at the circle. Let's draw two chords which are equidistant from the center of the circle. If you don't know the center of the circle, would it be possible to draw chords that are equidistant from the center? Yes, it's possible. Let's see how. If we measure the chords, we find both the chords are congruent. This means that the chords which are equidistant from the center will be equal in length. So even if you don't know the center, and you draw congruent chords anywhere inside the circle, they will be equidistant from the center. Based on this observation, we arrive upon a theorem. Equal chords of a circle are equidistant from the center of the circle. In the figure, we have two equal chords, AB and PQ. Let's draw perpendiculars from the center O to the chords AB and PQ. The perpendiculars are OM and ON, which also represents the distance between the center and the chords. Now to verify the theorem, we will prove that OM equals ON. A simple and quick way to do this is measure OM and ON using a ruler. First, let us measure OM. Now, let us measure ON. We can see that OM equals ON. This proves that equal chords of a circle are equidistant from the center of the circle. Here is a circle whose center is marked. Now the problem is to draw two chords so that they are equal in length. The challenge is to do it without measuring the lengths of the chord. Now, how easy is that? Actually, very easy. Let's discuss a theorem. The theorem states that the chords at the same distance from the center of a circle are equal in length. You can start by marking 2 points M and N at an equal distance from the center O. Now draw a chord AB passing through M and perpendicular to OM. Next, draw a chord PQ passing through N and perpendicular to ON. We have to prove that if OM equals ON, then AB equals PQ. Now, let us measure chords AB and PQ to see if they are equal. First, let us measure AB. Next, we'll measure PQ. Simple measurement shows that chords AB and PQ are equal. You just prove that chords at an equal distance from the center of a circle are equal in length. Do you know how we perceive sizes of different things that we see? How do we decide whether an object is larger, smaller, or equal in size to another object? This depends on the angle subtended by an object to an eye. The object that subtends a larger angle to our eye appears larger in size. If two objects subtend equal angles to our eye, they appear equal in size. Let us understand this better by using a triangle ABC. The angle at any of the vertices of a triangle is the angle subtended at that point by its opposite side. For example, angle BAC is the angle subtended by BC at point A. Angle ABC is the angle subtended by AC at point B. Angle BCA is the angle subtended by AB at point C. Consider a circle with a chord AB. If we join A and B with O, the center of the circle, then angle AOB is the angle subtended by chord AB at the center of the circle. Let us see how this angle changes if the positions of A and B change. What do we observe? As the chord AB moves closer to the center O, it increases in length. The angle subtended by AB at O also increases as the chord AB moves closer to the center O. As the chord moves away from the center, its length and angle subtended by it at the center decreases. Remember, we discussed that objects that appear in equal sizes subtends equal angles to our eye. Let us see if this is true for equal chords of a circle. The theorem states that equal chords of a circle subtend equal angles at the center. Here we have two chords AB and PQ that are equal in length. We have to prove that angle AOB is equal to angle POQ. In the triangles AOB and POQ, we know that AB equals PQ. Note that OA equals OP and OB equals OQ, since all these four-line segments are the radii of the same circle. Since corresponding sides of triangles AOB and POQ are equal, the two triangles are congruent by the SSS congruence rule. This also means that angle AOB equals angle POQ, since they are corresponding angles of congruent triangles. So we have proved that equal chords of a circle subtend equal angles at the center. Now let us see if the converse of what we just proved is also true. Theorem states that the chords that subtend equal angles at the center of a circle are equal in length. Consider a circle with center O and two chords AB and PQ such that angle AOB equals angle POQ. Now we have to prove that AB equals PQ. In triangles AOB and POQ, we know that angle AOB equals angle POQ. Note that OA equals OP and OB equals OQ, since all these four lines are radii of the same circle. Since two adjacent sides and the corresponding angles of the triangles AOB and POQ are equal, the two triangles are congruent by the SAS congruence rule. This also means that AB equals PQ, since they are corresponding sides of congruent triangles. So, we have proved that chords of a circle that subtend equal angles at its center are equal in length.